Hi everyone. I will be talking about graph sketching for a well-studied clustering problem called correlation clustering. This is joint work with Assadi at University of Waterloo and Aaron Louis Putterman at Harvard University. So as we know, the broad goal in clustering is to partition a data set into a small number of sets called clusters based on pairwise similarity information between these objects. A typical setup is that we are given a collection of n objects, a pairwise distance function defined over them, and a target number of clusters k. The goal is to partition these objects into k clusters so as to optimize the given objective function. Some well-known examples of objective functions that are used in practice include k-center clustering, where the objective is to minimize the maximum distance from any object to the center of its assigned cluster, or k-means clustering, where the objective is to minimize the sum of squared distances from each object to the mean of its cluster, and so on. Roughly 20 or so years ago, Bansal, Blum, and Chawla introduced a new take on clustering, which they called correlation clustering. In correlation clustering, instead of having a distance function over objects, we are only given some qualitative information for each pair of objects, namely similar or dissimilar. We can now think of a clustering instance as described as a complete graph where every edge is labeled either by a plus or a minus. Pluses indicate similarity and minuses indicate dissimilarity. This formulation was motivated by the fact that this qualitative similarity, dissimilarity information is much easier to obtain than a precise distance metric over the objects. And in many applications, this turns out to be already sufficient to obtain a high quality clustering. So formally, in correlation clustering, we are given a complete graph where the edge set is partitioned into positive edges and negative edges. And the goal is to partition the vertex set of the graph into clusters so as to minimize the number of positive edges that go across the clusters, plus the number of negative edges that remain inside the clusters. So we seek to minimize number of similar objects that are separated by the clustering, along with number of dissimilar objects that get clustered together. An important feature of this formulation is that there is no pre-specified target number of clusters. This information in this formulation is meant to be revealed by the intrinsic properties of the input data that's being clustered. Okay. So since the introduction of this particular formulation, correlation clustering has found many applications and has been extensively studied. So one typical application where correlation clustering is used is deduplication of records in a database that is aggregating information from multiple sources and hence may contain multiple versions of the same record. So in this application, it's easy to see one wouldn't know a priori the number of clusters of interest because that corresponds to number of distinct records in the database. And also, it's natural to think that the qualitative similarity and dissimilarity information is sufficient to cluster together similar records. So before going any further, let's work through a toy example, which will also help me set up the particular way in which we will view the problem, along with some notation that I will use throughout my talk. So from here on, I'm going to assume that the input graph is simply the graph of positive edges, and the negative edges are implicitly specified as the non-edges in the input graph. And a clustering is a partition of the vertex set into clusters v1, v2 to vk for some positive integer k. Given any such clustering, its cost is simply the sum of number of edges in G that go across the clusters v1 to vk. So recall that these are the positive edges, plus number of non-edges in G that are inside these K clusters. We'll denote this cost by cost sub G of V1, V2 to Vk. And the goal is to find a clustering that has a minimum cost. So here is a sample clustering of the graph shown on the right. It partitions V into two clusters, V1 and V2. And the cost of this clustering is 2 because it has a similarity edge going from V1 to V2. So this edge has been cut by this clustering. And it also has a dissimilarity edge inside the cluster V1. Okay, so what do we know about this problem? Early on, it was shown that correlation clustering is APX hard. On the other hand, the work of Bansal, Blum, and Chawla already gave a constant factor approximation algorithm for this problem. Since then, the focus has been on identifying the precise constant approximation ratio that is achievable for correlation clustering. And as you can see, there has been considerable work on this front in just past few years. At this point, the state of the art for correlation clustering is a polynomial time approximation algorithm that computes a 1.437 approximation ratio. And based on the recent history, it wouldn't be surprising that this number would come down further in another year or two. Okay, so while the work on understanding the precise approximability of correlation clustering continues on, a parallel line of research has emerged that focuses on solving this problem on large graphs using sublinear computational resources. So correlation clustering has been studied in many different models of sublinear computation, including the streaming model, where the instance is revealed as a sequence of edges, and the focus is on designing a small space algorithm. Query model, where the input graph is accessed via queries and the focus is on designing a sublinear time algorithm. And the MPC model, where the input graph is partitioned across multiple machines, and the focus is on computing a high-quality solution using a small amount of communication between these machines. Just like the classical setting, there has been a huge body of work on approximating correlation clustering in the sublinear setting, especially in the past few years. Let me just mention a few highlight results. In insertion-only streams, it is now known that n polylog space suffices to get a 1.84 approximation. In dynamic streams, n polylog space suffices to get a 3 approximation. And in the MPC model, we can get a 1.87 approximation in constant number of rounds. All these results adapt and extend ideas from classical algorithms so that they still work well in these highly constrained settings. And these adaptations tend to be model-specific and do not typically keep up with the advances made by the classical algorithms for correlation clustering. So the motivating question for this work is the following. Can the gains made by classical algorithms be ported over to the world of sublinear algorithms in a black box manner without losing anything along the way in terms of the approximation quality? There is a very natural approach that's a candidate for achieving this goal, namely graph sketching. This is a technique introduced by Ahan, Gua, and McGregor, and the main idea here is to create a compressed representation of an underlying input graph by taking a small number of linear measurements. These measurements are referred to as a linear sketch of the input graph. Since linear measurements compose together, linear sketches naturally lend themselves to designing dynamic streaming, MPC, and distributed algorithms. And in fact, the graph sketching paradigm has been quite successful in solving a number of interesting problems with a small size sketch, including cut and spectral sparsifications in graphs, matchings, and vertex connectivity. The gold standard for graph sketching solution is to have n polylog n size sketch, as it is easy to show that for all problems mentioned here, including correlational clustering, any sketch that allows you to recover a good quality solution must have omega n size. So this raises a natural question. Can we efficiently solve correlation clustering via an n polylog n size graph sketch that allows us to match classical approximation guarantees? Our main result is that indeed the answer is yes. In particular, given any n vertex unweighted simple graph G, there is an n polylog n size linear sketch which allows us to recover an alpha best correlation clustering solution in polynomial time. Here, alpha best is the approximation ratio of the best classical approximation algorithm for correlation clustering. So if this ratio improves, our theorem would allow us to use our linear sketch to get a new algorithm which recovers in polynomial time a solution of this new improved quality. And once we have this main theorem, it has immediate applications to sublinear algorithms. So for instance, it gives us a dynamic streaming algorithm that uses n polylog n space and matches the best classical approximation ratio. Similarly, we can also get a constant round MPC algorithm that matches the best classical approximation ratio. So in the remainder of my talk, I will present a high-level proof sketch of our main result. Okay, so let's start by briefly reviewing a relevant tool, which is the notion of a cut sparsifier of a graph. Given any graph G and an accuracy parameter epsilon, a 1 plus minus epsilon cut sparsifier of G is a subgraph H that preserves the weight of every cut in G to within a 1 plus minus epsilon factor. Note that we would want the sparsifier H to have much fewer edges than the original graph G. So this means that even if the original graph G was an unweighted graph, the sparsifier H must necessarily be a weighted graph in general. There is a beautiful result of Bengzur and Kargar from almost 30 years ago. It shows that every n-vertex graph G admits a cut sparsifier H, which has only order n log n edges. Moreover, one can assume that the sparsifier H has the same total edge weight as the graph G. That is, H is a weight-preserving cut sparsifier of G. Our starting point is a simple lemma that shows that any weight-preserving cut sparsifier contains enough information to solve correlation clustering almost optimally. In particular, what the lemma shows is that for any correlation clustering solution, its cost in the original graph G and its cost in the weight-preserving cut sparsifier H differ only by a 1 plus epsilon factor. So at least information theoretically, a weight-preserving cut sparsifier has all the information needed to get a 1 plus epsilon approximate correlation clustering solution. I should note here that similar statements have appeared in previous works, but not in this exact form that we need. Okay, so this lemma suggests a natural plan. AGM already gives us an n polylog n size linear sketch to build a weight-preserving cut sparsifier H of a graph G. We can now simply run the state-of-the-art classical approximation algorithm on H to hopefully recover an alpha best approximation. Unfortunately, there is a catch, and it's a rather big one. The sparsifier H is a weighted graph, And correlation clustering on weighted graphs is a much harder problem to solve than the standard correlation clustering, which is defined on unweighted graphs. It is, in fact, equivalent to the multi-cut problem, for which no constant factor approximation algorithms are known. So we will try a new plan to get around this obstacle. The first step of the new plan will be to build a weighted cut sparsifier H as before. But now, in the post-processing stage, we will use this weighted cut sparsifier H to recover an unweighted graph G prime that also happens to be a cut sparsifier of the original graph G and contains the same number of edges as G. So G prime is a weight-preserving cut sparsifier of G that happens to be unweighted. In other words, we are desparsifying the sparse weighted graph H to recover G prime that is as large as the original graph G. We can now run the state-of-the-art classical algorithm on G prime to recover an alpha-best approximate solution. It may seem counterintuitive, but we are gaining efficiency in this process by blowing up the size of our cut sparsifier. So let's look at the new plan in a bit more detail. So step 1, we build a weighted cut sparsifier H as before using the AGM sketch. In step 2, which is happening in the post-processing stage, we solve a linear program in polynomial time to recover a fractional graph H prime from H that is the weight-preserving cut sparsifier of H. So each edge in H prime is assigned a fraction between 0 and 1, and these fractions add up to the total weight of the edges in H. In the third step, we round this fractional graph H prime to obtain an unweighted graph G prime, such that G prime is the weight-preserving cut sparsifier of H prime. There are some technical challenges in implementing this plan, but at a high level, this is indeed the entire algorithm. So let me finish by visually recapping the algorithm. We start with the input unweighted graph G. We then use a linear sketch of size n polylog n to create a weighted sparsifier H. Then in the post-processing of the linear sketch, we solve a linear program in polynomial time to create from H a weight-preserving fractional cut sparsifier H prime with the same edge mass as H. And finally, we round H prime to create an unweighted sparsifier G prime of the original graph G. We can now run the alpha-best approximation algorithm on G prime to recover a solution for the original graph G with an identical approximation ratio. So here is the entire process summarized in one picture. Okay, so let me conclude with a few final thoughts. We showed that there is an n polylog n size linear sketch for correlation clustering that allows you to match classical approximation guarantee in polynomial time. Our algorithm uses n polylog n space in the sketching phase, but it uses polynomial space in the post-processing phase. So an exciting direction for future work is to figure out if one can do post-processing also using only n polylog n space. Thank you.